We will do today is to talk about more about combustion, because we identified that combustion was one of the main reasons for most of the air pollutants that you see in the atmosphere. Okay. And we'll quickly see what you have done probably in your undergraduate when you were looking for the thermodynamics or the engines. A little bit of engines we all study irrespective of what the branch you come from. Okay. So we all understand there are two-stroke engines, there are four-stroke engines. Two-stroke engine also you can have a little feel. Two-stroke engines are a little dirtier. Okay. Because we are not giving enough time for the combustion to complete and not getting the equivalence in the process. But anyway, let's have a quick look on to the four-stroke engines that are spark ignition engines. In fact, in India, you will be, I don't know how much you know, there's a decision has been taken, a policy decision that we will not produce any more two-stroke engines. So I would like that you recall the two-stroke engines and four-stroke engines, and within that there are two kinds of engine, which is spark ignition engine, and one is the compression engine, or that can be ignited on its own. Okay. And when we talk about the compression ignition in internal engines, these are largely the trucks, the buses, the locomotives, the ships and all. Okay, but this also, there's some large engines, okay, which are compression engine, but they may also be two-stroke, but they are very, very few. Apart from that, we should understand, at least recall, that they're kind of four cycles, okay, 4 strokes: intake, compression, expansion, and the exhaust. Okay. So don't read so much in here, because there's a little figure which we all will recall that's much better and easier to understand. So the first stroke is that intake. So what you see on the top of this is the intake valve. Okay, the fuel is withdrawn. Okay, and the piston is moving down. Okay, and this is the outlet or exhaust. You see that is closed here because there is a closing here. Okay. Once this is completely filled, okay, which is air and fuel, then the compression starts. So this time the piston is moving up, and both are closed. See here the intake is also closed, and the exhaust is also closed. The little line, you see that one here. Okay, so we get a compression stroke, and then there is a power or expansion stroke. In that case also, both the valves, inlet as well as outlet or exhaust, should be closed. So this is closed, and once you have the exhaust, inlet is closed, okay, the exhaust should open and things move out from there. As a result, the cycle goes on, and then we continue to get the power stroke. And you can also see that this position where the theta is 0, theta is the angle, okay, or called the crank angle between the piston rod and the crank rod, and then this is called as theta. So when it is in this position, this is called top dead center, we all know that. So then theta is 0, theta is whatever the angle is, that is theta. When it is at the bottom dead center, the theta is equal to 180. Okay. In two-stroke engine, there will be only 2 strokes, but most of the time now we in India, we're talking about mostly about the 4-stroke engines. In fact, all scooters even you see, they all have been converted to the 4-stroke engines. Okay, because we'll probably see in the lecture that 4-stroke engines are cleaner than the 2-stroke engine. Okay, in 2-stroke you get the power very quickly. Every second power you're getting, every second stroke you're getting the power. But in 4-stroke, the kind of pickup that you have on the scooters, those were 2-stroke, Priya and all, they'll be much more than the other scooters. But the technology is changing very rapidly in this case. We don't want to be expert on this one, but still we want to understand few things. This is the same thing, that's what we described. okay, the top dead center, the bottom dead center, and the crank angle. And sometimes the emissions also depends on the position where the piston is. So we'll pass on this to you, so you don't have to worry about this. Okay. I want to tell you a little bit about the fuels now. Not so much into the details, but what are the fuels? We all know natural gas or CNG. Okay, the compressed natural gas. You all are seeing that there's kind of a revolution that more and more people are using CNG now. And earlier, most of the time, it was gasoline, but you see the CNG has become very popular. CNG is largely methane. It's a very clean fuel, simple and safe. It's not proper. Somebody says it is not safe. It is safe. The burners that you require to burn CNG are the very cheap burners, because the cost of the burner sometimes is exorbitant. Earlier problem as to why the methane was not used was the largely problem with the storage and the refilling. Okay, it was not easy to store it in the at the petrol pumps or in the engine, and the refilling was a more problem. Like how do you refill the whole things? But these problems have been taken care with the technology, and now you can find more and more outlets. See, it takes a while. See, first of course you bring the pipeline, and then the transport through the trucks is a little difficult, and moreover, then how do you transfer the CNG? That was the problem. The other associated problem with the natural gas, when it comes out, okay, when it comes out from its source, it is, a significant amount of H2S along with this CO2 and the nitrogen, and H2S especially, it must be removed, okay, and it must, sometimes the H2S can be in percentage, okay, and just imagine in percentage. Suppose and there is a plant which has dealing with methane production, and some leakage is there. So methane, as such, leakage of the methane in the atmosphere, because there is already significant amount of the methane is there in the atmosphere. But if the H2S leaks along with this one, there will be hue and cry. People, this H2S, the order threshold is as low as 40 micrograms per meter cube. Little amount of methane, and then the person are uncomfortable. They may find, oh well, there's something terribly gone wrong, when H2S can be in percentage. So earlier, because of these problems, and then the storage and the transportation, these are little problems for people who were not using methane. In fact, in many of the oil fields, methane was simply burnt, okay, because they were interested in the liquid product. But things have changed with technology, and then we are using lots and lots of CNG. Liquefied petroleum gas that we use in houses, is largely the propane, okay, and it's clean fuel, simple, safe, cheap burners, easy to store and refilling. Because see here, this you cannot liquefy CNG, okay, whereas this you can liquefy because it's a high molecular compound. You can liquefy this and store it, and then in the right at the atmospheric temperature, it can be with the pressure that you are dealing with, so it can be liquefied as well as in the vapor phase also, okay, and then therefore you can use this, and it's easy to store, refilling, and many things are using the LPG, not in houses, even in the automobiles we have started using LPG. The both reasonably burns well, but methane is directly available at the source. Wherever you are doing the like the exploration, methane is a product along with the liquid crude that you get, and LPG is to be produced and processed at the plant. LPG will not come out because CNG is in the gas form, and so it will come automatically. But the LPG are produced in the refinery, and the problem with LPG is the little bit of refilling is a problem. Okay, so you see this the people you go at the CNG outlets, they are able to fill the CNG for you. But LPG is a exchange the cylinders, okay, because you can't do the refilling of LPG so easily, because this needs to be liquefied and stored and things like that. Well, this little bit reminds me, suppose you are doing, like at home we are there, and suppose what happens is really this, you have the LPG cylinder. Well, we are drifting from our topic, but well, let's drift. That is the storage. This is really in the LPG is really liquid inside, and there is a vapor above this, so it has a vapor pressure. okay, and then what you're taking out is this, the vapor constantly comes out, okay, and then you can, this vapor you are burning. So this is the problem, that since it is a pressure that is maintained by this thing, okay, and the pressure is always the same, okay. So problem with LPG in the household, you will never know when LPG cylinder is likely to be emptied unless you have put it onto the weighing scale, okay. Suddenly, you know, we all know that housewives are suddenly, oh, the gas is finished, okay. Gas is finished because what, the pressure is always there here because of this, okay, and then pressure is not reduced, but suddenly as this goes by, the pressure is still maintained, and then this disappears suddenly, I mean, you know, like, and then they might say, well, all right. And how did this very simple mechanism, it takes the heat from the surrounding environment, okay, and then this becomes in the vapor phase, and that is what you need is the latent heat basically, it takes from surrounding. Suppose you run into the problem, try this, okay, you run into the problem, and suddenly suppose your mother or your wife or whoever you are working with, so the gas is finished, okay, and then you can, or you might have even observed, you know, these shopkeepers, you know, like restaurant people, they will not keep it vertical. Of course, you should keep it vertical. They'll put it upside down, okay. And in the winter especially, if you can put a little hot water onto this, not very advisable thing, but in the emergency, you put hot water onto this one, lay it down, and put little hot water, because hot water you can get from electricity or whatever, or you have the hot water somehow. You put this in, you might still be able to reuse the remaining little liquid that you have, because that was not able to vaporize, because, you know, like, you need little heat in that area, and then you have laid it down so that, you know, the pressure is built up onto this side, and then this can vaporize, okay, because this is a liquefied gas, and you can still use it. So just, or even if some people wrap the clothes or something and put a little hot water and things like that, and then this, your LPG thing will work a little bit longer than what ordinary is. Anyway, okay, but now people have the ways that they can directly, even from the petrol pump, you can directly fill the propane into your vehicle and things like that. Of course, the other stationary combustion, you know, people do use this one easily. Let's also talk about the solid fuels. Okay, this table I'll pass on, but just have a look onto this one. What is the solid fuel? Because the major problem of air pollution largely is from the solid fuel. Okay, and then as you see, coal and oil and things like that. So this is a little analysis that is taken from a book. Okay, so you can burn the wood, peat, lignite, subbituminous and bituminous coal, and then you see it is a as the coal is the aging process happens, the carbon content goes up. Okay, all right. So you have the wood, you have both carbon and hydrogen and oxygen. Some amount of nitrogen is there, and some amount of the sulfur is there. And the ash, of course, is a very significant part. Okay, sometimes the ash, these are the typical numbers. It can vary significantly depending on the what source we are talking about. There are coals which may have the sulfur content as high as 4%. Okay, there are coal from certain seams which may have the ash content, or especially the bituminous coal, ash content as high as 50%. Okay, but we still burn them because we need the energy. So here, and therefore the coal will have many things other than the carbon and hydrogen which can burn. So you have the solid fuels will have you lots of emissions of the ash, okay, lots of emissions of the oxides of nitrogen, and also lots of emissions of the sulfur dioxide. Okay, so here what you need to see is the carbon, hydrogen and oxygen and nitrogen and sulfate. So when we want to reduce the carbon dioxide emissions, okay, when you want to reduce the carbon dioxide emission, obviously these fuels are no good, because see, nowadays people are looking very comprehensively that what kind of fuel we should use to reduce the CO2 emissions because of the global warming and things like that. Okay, some of the students you may know is so now you can trade. This also becomes a factor that we want to use this coal or this coal for that matter. Okay, because the emissions of the carbon dioxide will be much lower here. Okay, And this is a general formula for getting the heating value of the coal in terms of the dry values computed from the equation is this one. The higher heating values, that is British thermal unit per pound, okay, you can always do the conversion, is times of the carbon and times the hydrogen minus oxygen, okay, because if the oxygen is more, that is not going to burn, plus this quantity with the sulfur. But this becomes very, very small in terms of the heat value, okay. But this also, the sulfur can burn, okay, and it can give you some heat, because this will be in a very, very small quantity. So just do some calculation. We here, we have some values here. Average wet basis delivered this in US, okay. Heating values are given here, and then okay, this is on the dry basis. So I don't know if you want to try this, and if you see that you'll get this number to indicate as to how much heat will be available. Okay, so depending on your source, you can use. Why I'm talking about, especially about the carbon content, is well, it's quite related to some of you know, but let me also. We all know about we have to reduce the CO2 emissions and all. One of the technique is the CDM. In this case, the rich countries can invest in developing countries in terms of low CO2 emission technology and get okay, you can get the carbon credit. Okay, here idea is that, well, suppose I say, well, I have mostly anthracite coal in the country and I am going to burn most of the anthracite. Okay, I am a developing countries, I have no choice, I have to still have to develop. So suppose some country come forward, well, all right, please don't burn this. Part of the coal will supply you with the better coal, which has a low carbon and things like that. So then the CO2 emission will reduce, but the reduction in the CO2 emission that will occur, that will go as a credit to the other country. Okay, that's called as the CDM. So there's a mechanism that, you know, like you, and CO2 is a global issue. Wherever you can control, that's to the advantage. Okay, so that's what I wanted to tell you, that about the fuel and things like that. And let me also tell you that the SO2 issue which you see here, SO2 largely is in the organic form, and it can even burn much before the carbon will burn. Okay, so the moment you fire, okay, you might not be able to burn some carbon, and then carbon may appear in your ash, but sulfur will never appear in your ash, because sulfur will quickly take off and burn. Okay, that's very, very important to understand, because sometimes people will say, well, or some sulfur will be in the ash, some sulfur will not burn, but most of the I should not say sulfur, you should say sulfur is in. So one of the first thing to burn is SO2. Okay, so you should have an idea of the fuels, what is peat, what is lignite, and what is wood, and things like that. And See, the wood has very low ash content and things like that. But then again, the energy per ton of coal is more here. It's a little bit like, as compared to what we burn in India, it is a little bit on the higher side. Okay, because in India we'll have the ash content will be very, very high here. Okay, so these are not the picture from the. Are we burning lignite somewhere in India? Yes. Navali Lignite Corporation, they have a huge power plant based on the lignite. Okay, and the other uses also they have for the lignite. Okay. Okay. Still talking about the engines and things like that. So the emission depends on the air-fuel ratio that we'll examine in details. Ignition time, compression ratio, combustion chamber geometry, engine speed and type of fuel. Okay, that's where the pollutant emission will depend on the internal combustion. Okay, some of them we'll see and some of them we will not see because it depends as to what extent we want to go. We can skip this slide because that's what I don't want to discuss so much. The pollutant in the combustion process is, well, alright. Nitrogen oxide, CO, hydrocarbons and soot and sulfur dioxide you can add, because sulfur dioxide is also a very, very important issue. Okay, let's see how it is happening. Let's talk about the nitrogen oxide because that's a very serious issue we have. And then let me also define phi. Okay, you remember that we defined the equivalence ratio last time? Okay, what was that? If you wrote that?
Fuel air ratio actual divided by fuel air ratio estimate.
Okay, so that is what is again? Is that the same thing? The equivalence ratio? Okay, now quickly tell me if the equivalence ratio is less than 1. Am I on the leaner side or I am on the richer side? Leaner side, okay. Alright, if that is the case, let's have a look onto this one. So we have defined the phi. So when the people look in the actual thing and try to give the reason behind this one, when is the peak NO? Because NO is only formed. Happens is when the slightly lead of stoichiometry when phi is close to 0.9. So if it is on the leaner side, so here you see the peak is somewhere, the NO peak is not here at stoichiometry, or it is here, somewhere here. Okay, somewhere here is the formation. Okay, because of the oxygen surplus is there. Alright, we can keep on, then in that case, this as we are talking about the excess oxygen, it does not necessarily that NO levels will continue to go high because as you increase the emissions. Okay, why? Because you need certain temperatures also. So what happens? It is very sensitive to the temperature. Okay, because you need high activation energy. Okay, so in the process when you are going towards too much on the leaner side, okay, because you are not supplying enough fuel, so temperature will drop. The temperature drop, then NO will not form. Although you may have lots of oxygen, because as you are moving this side, you are having more and more of oxygen or the excess oxygen onto the side. But there are two combinations required. You should have the excess air, but also we talked, and the high temperature. So when you want to manage the things, you can either manage by controlling the oxygen or by controlling the temperature. Okay, that we'll see maybe today or maybe in the next class. Now there is a terminology here very quickly. You see prompt NO. Okay, that we will see in a moment, but stay with the term prompt NO. Prompt NO is that NO which is formed first. Okay, and we'll see that how that is formed. Before you can think of anything else, the prompt NO happens, and these methods with thermal NO is was devised by Zeldovich. So that's sometimes called Zeldovich NO. Prompt NO, or the person identified this one was Fenimore. Okay, and then it could be due to oxygen atoms that in the flame front, or due to carbon and hydrocarbons and C2 molecules in the flame which is the front. So what happens before even nitrogen and oxygen of the atmosphere can react? What you see here is that this thing can occur, and you will see that even this hydrocarbon can react to some extent with the nitrogen and can produce nitrogen dioxide. Okay, earlier what we were talking about just N and O. Okay, but here That is fine, that is one route. Okay. So what you see here, the one route is, of course, if you have the O, if you have this, okay, then this can be quickly be formed. Okay, because the activation energy requirement is, this is the slow process. Okay, activation requirement is high, and if you can, with this, it can react and it can form NO, and this activation requirement is reaction is much faster. Okay. Zeldovic occurs in the burnt gases, okay, because when excess everything has happened, okay, because this reaction of formation of N2O2 is slow, burnt gases downstream of the flame front and not in the flame front itself. Okay, but this does not tell us the whole story, because something else occurs right in the flame. Okay, and what happens? Experiment shown that the sum of NO forms inside the flame. Okay, that is called the prompt NO. Okay. And then it may not depend on temperature, it may not depend on to the nitrogen in the fuel. Okay. We'll show you the plot of NO versus distance from the flame, extrapolate back to the flame front location NO. This is defined as, this picture I'll show you in a moment. Experiments show that the prompt NO is more prevalent in hydrocarbon flames, okay, and for fuel rich flames. Okay. Even if the fuel is rich, even though the less oxygen in the rich fuel, thus in this situation, okay, where for the prompt NO, okay, this is not very important what is the temperature and things like that, but the reactions that may occur, okay, you see here when the people plotted this, okay, they were like, they found that there was a quick NO level and then stabilized. That was more because of the thermal NO, okay, as we moved away from this one. So initially, see, the point I'm trying to make here is that for this formation, okay, it doesn't even need that you have the excess air or not. Okay, that oxygen which you are supplying even for the combustion, part of it, very small amount, part of it might just be taken by the nitrogen there. And how it happens is that you have some hydrocarbons. With this hydrocarbon because there are the two routes, possible routes, okay, still people are discussing into this one how it happens, that this hydrocarbon can react with nitrogen also, okay, which is there in the along with the air, okay, and it can make the atomic nitrogen, okay, and this atomic nitrogen can react with oxygen, okay, and this reaction was, if you recall from the last slide, this reaction was faster or slower? Faster. Much faster. Okay, so you get here this is for, so this reaction can happen and you can get some NO. Okay, because the is much faster than the route from N2 plus O. Okay, or some people also say that, well, some carbon may be available for the nitrogen to form CN, followed by CN can react with the oxygen to give the CO and NO. Okay, so this also can happen. Okay, so that you also can see, although you may have lots of oxygen, but you may still produce CO in that process. But most likely process is this one, that you can get the prompt NOx. But there's nothing much you can do about the prompt NOx. That will be formed. I mean, that you can't do much about that because this happens right in the flame. People are looking at the ways and means to control the prompt NO, but that again is not very significant amount. I don't really know how much it is, but it could be as low as 2%, 3%, 4%, that sort of thing. Okay, so the new thing that you learned is the prompt NO, and that is formed because of the reaction between the hydrocarbon before it can be taken up by the oxygen, between the hydrocarbon and nitrogen. Okay, that may produce atomic nitrogen, and that can very quickly react with the oxygen before even this oxygen can take on to hydrocarbons. Okay, so that's what is called the prompt NO. Okay, this is a little picture which you should let's spend some time onto this one. So here, this is what is people did two experiments. Okay, how to say that how much can be thermal NOx and things like that. So here you see this one, first they did with a normal oxygen. Okay, and they were burning petroleum derived fuel, the shell fuel, the coal derived. So you look at the coals as little squares as you see there, 1, 2, 3, 4 and things like that. Okay, so they they did a regular operation. Okay, and then he said then the nitrogen content in the fuel was there. Okay, and then what was happening was the next time they did the same experiment with different fuels with different nitrogen content, but this time what they did, they supplied pure oxygen, or pure oxygen along with the argon. Okay, so obviously the NOx formation will be much less, right? So this is, or probably it should say the same thing. The lower curve shows the fuel nitrogen conversion as determined by the substituting an argon oxygen mixture for the combustion air. So obviously it will be only the fuel NOx that will be formed, and so that with the difference they could find out that what is the quantity of the, okay, the total, this will be largely with the thermal NOx. Okay, and that is what probably you can control, or you can try to minimize this NOx as opposed to the total, as opposed to the NOx that may come out from the fuel. And then you can also see that, well, this thing is higher for the coal, somewhat higher than the coal that you will see here. So well, this is here, okay, this is here, and corresponding value should be somewhere here, because they all have to have one-to-one correspondence. And then you see the coal. Coal is in fact a very significant source of oxides of nitrogen. Okay. Okay, so this gives you a little idea that as to how the people could figure it out, that part of this one was the NOx and this and that. Okay. This is another picture which is very similar to what we have shown you earlier, is that it is the something. Now this is, I'm not talking in terms of the, it's a reverse, same thing. Okay, here we are plotting air to fuel ratio, and that's what we are talking about, the equivalence ratio. Equivalence ratio will be something like reciprocal, okay, of the two ratios, AF by and this and that. So again this peaks at this point, okay, at this point. And so if I have to plot stoichiometry, where will be the stoichiometry? The stoichiometry will be this side or this side? How? This you have to answer. Stoichiometry has to be on which side? Left side. See the one on the top, right? That is stoichiometry. Because equivalence ratio is fuel to air ratio actual divided by fuel to air ratio stoichiometry. Okay, if it is 1, it means we are at stoichiometry. Okay, so here you see here, as onto this side, as we are going in terms of the air to fuel ratio, as we go put in more and more air, okay, the NOx formation is more and more. Okay, then why does it decrease? Because although there is more nitrogen, more oxygen, but then your mixture is becoming so lean that the temperatures that you are getting is not very high. The temperatures are not high, then in that case, you know, like it will tend to decrease, because you need both. You need the temperature as well as you need the excess oxygen. Okay, very funny, but very, very important graph. Okay, it is the same thing, and it's more of a mechanism as to the formation. This is the same graph that we need to understand. Okay, it's showing both NO and NOx. So you see here largely it is NO. Okay, a very small amount of NOx can be formed depending on the equivalence ratio that you have. And then as you are increasing the equivalence ratio, it will peak until 0.9 or something, okay, and then this will come down. Okay, let's talk about the unburnt. We are not talking about the control, we will talk control in the next class, but let's talk about the hydrocarbons. Okay. Okay. In the engine, emissions of the unburnt hydrocarbon comes from the raw unburnt fuel, because some fuel can escape unburnt. Fuel that did not burn all the way to CO2 and H2O. Okay. some might just escape as such, okay. Some might escape, they are converted into something else but stayed as hydrocarbon but did not burn, okay. Because you see, you start with some hydrocarbon, then they are the intermediate oxidation of the fuel that can take place. So you started with, let's say, with methane for that matter. Some may burn directly and some it may convert, something like okay. And then what you might find that some might just go this as unburnt, and you may find this could not burn in the process and this was never in there, okay, but this might also be seen at the exhaust, okay. So that is the difference between raw unburnt and fuel that did not burn all the way to CO2 and water. Lubricating oil is a serious problem, okay. Lubricating oil that we all use in engine is, especially in the two-stroke engine, which is using the fuel plus oil mixture, okay. So what happens is that in the two-stroke engine, if you recall, what we do, we put the lubricating oil every time along with the fuel. I don't know if you recall. I mean, the old scooters, you go and they say, okay, 2 liters petrol, 30% or 3% of that was lubricating oil that you keep always add from outside, okay. And in that case, you are adding the lubricating oil, okay, especially in the two-stroke engine, and sometimes the lubricating oil cause lots of emissions, because in the process that can also get, that can also get burnt and can give the fumes out. I don't know, is anyone from Delhi here, or have you seen the petrol pumps in Delhi? See, what they do is that they have earlier what people were doing, they'll put the oil from outside, okay, the lubricating oil. That may be dirty, or people had the tendency of using more oil. They think, oh, there should be better lubrication, okay. But you don't need more oil. More oil can be more problem, okay. So it can be raw unburnt fuel, it can be fuel that did not burn all the way to CO and H2O. There could be lubricating oil because of the two-stroke engine, that emissions are more because that people put more and more lubricating oil, okay. And then other than the tailpipe, which are more or less these things. So I was giving the example in Delhi. So Delhi, they have banned that you can't put the lubricating oil from outside. So there's a dispensing machine along with the petrol machine, petrol delivery pump. You put this one and then it'll put dispense exact amount of the lubricating fuel in there. You can't buy it from outside and things like that. Other than the tailpipe, there's the crankcase fumes, okay. That can come out. Fuel tank, older cars, they didn't have any evaporative emission control system, and filling stations in the region with 2-second hose to recover the gas tank vapors, and the tires also we know also give the lot of organic vapors, but that is not from the combustion sources. Maybe it might be a good idea that I don't leave you thinking, we might talk about this thing a little bit later, but I want to give you a little feel of this emissions here. The crankcase fumes, okay. Okay, this is a piston, okay, this is inside the cylinder. At the piston, what do you find? Round thing. You always find piston rings are there. Okay. Okay. If you have the piston is here. Okay. The piston rings. Okay. Not a very good picture, but what is the role of piston rings? To keep it tight, they are a little flexible, they can, press, okay, and then they really expand themselves so that it becomes a little fixed. Okay, what happens when you have the piston rings here? Okay, as the engine gets old, there is a wear and tear of everything. Of course, there are two metal parts hitting each other all the time. Okay, So what happens with this thing's worn out, and the piston rings also worn out. Okay. So as a result, when you have the expansion stroke or power stroke, okay, as you are getting this one, so the huge pressure here, okay, and this, because of this pressure which is very high here, this things, because of the wear and tear, this hydrocarbon, as even before it burns or partially burned, it can come out from the space here and then come out in the crankcase. This can also come from the side also. Okay, and obviously once this comes out, there is no way that you can burn it. Okay, so this is called the crankcase emissions, or more popularly known as blow-by emissions. See, combustion engineers or IC engine people, they will be expert on everything, but we need to know at the air pollution level what are these emissions and why the crankcase emissions can be of huge significance. Okay, maybe we'll talk about the control of this thing maybe in the next class, but the most of the control that they do is the blow-by emissions are recaptured and recycled in the car only. But at least now you know that this is what we are referring to, the crankcase fuse, older engine without crankcase gas recycling. Because if you can recycle this emissions back in there, well, you are more or less handling the situation. But if you don't, then these emissions used to occur. So therefore you say, all right, the old guy, you know, like you must get the engine done well, the maintenance is very important and things like that. And sometimes, you know, the old engines can go so bad that then there's a government regulation sometimes, well, more than 15-year-old engine should go out of business, you know, because these emissions can become very, very significant. And this will be all the emissions of the hydrocarbons. You can also see the fuel tank emission. Maybe we'll talk about a little later about the fuel tank. But if you have the car, well, I don't know how good or bad the car looks like. Okay, let's see if this is the front. You have the light on this side, and then you'll have the fuel tank here. Okay, so when they used to fill this thing, you have the petrol is up to here. Okay, as you are filling, so the pressure here builds up, and then there is the leakages from here. Okay, so this is called as the evaporation losses in the tank. Okay, but now of course, and then this can occur all the time. Okay, it's not only when you are filling it up, that time it is more because you have opened the wall, and that is time the emissions are more. But this occurs all the time. There will be some leakages, this, that, and even if you know, like even if there are no leakages, you can see where in a petrol vehicle where this fuel is taken, fuel is pumped through the fuel pump. It's taken to carburetor. Of course, the new technologies have changed, but the old thing, you'll have the carburetor. And carburetor, what you do is it kind of vaporizes this one, and then you mix the oxygen with that one. That is why you think. So even if you know, like your pipeline is open, okay, as the fuel is going to your carburetor, and this engine is hot, okay, the fuel continues to go there, and then this is the liquid, but then it can evaporate from here, and then there could be constant emissions from here. Okay, that can be just evaporation. Okay, because unless the whole thing is, you know, cool off and things like that, and then there can be emission. So at least some people used to say, like earlier scooter, the moment you are off the scooter, then you switch off this one, so that at least this thing doesn't go anywhere. But now what these people are doing is that, probably we'll see in the next class, is that they are able to recapture these vapors, okay, and put it back in there. Okay, so that you can completely recycle. We'll probably see one line diagram, because you should know, have an idea what the latest thing people are doing. And I don't know if you notice this thing, that as you are driving, and then you say, okay, your car is showing, you know, the empty kind of thing. Okay, and then we're all right. You stopped somewhere for half an hour, 1 hour, or this thing, and this thing slightly going back, and saying as if you have more petrol in your car. Okay, this is all captured by your operation system. Is very complicated. The amount of research and development that has gone in the car, okay, I think there's no other machine where the changes of the technology have so many efforts, even from the comfort to the combustion to the air conditioning and to the heating, and then you can adjustment of the seats. They are like, sometimes the seat there are 4 or 5 motors that you can adjust your back for, this, that, I don't know, everything you can do there. But so this all, everything is there. So otherwise, if you don't, these things didn't have, so they will also have very significant emissions from this thing. Okay, and filling stations, of course, they have to have sometimes the system that they can capture even at the filling stations and things like that. So you see the source of hydrocarbon that comes. Okay, all right. Well, we will do this one. Okay, and you really need to put some attention here because this is a very interesting and useful figure. Okay, so what I'm trying to do is that, well, I'm running the engine and trying to see what is happening in the exhaust, and I'm running the engine, let's say, for the different conditions of the air to fuel ratio, and trying to look at the 3 important things, because carbon monoxide, hydrocarbon and NOx, and their concentration can definitely look very, very different. And you see, be careful about the units. CO is in percentage, okay, hydrocarbon is ppm, it can even be more, okay, and the NOx is again in ppm. Okay, so let's see. Thanks to Bara, he has put this animation into this one. So for example, our stoichiometry is here. Okay, and then I started, put my engine on, and then you see the CO. Okay, so in this region I'm not putting enough of the oxygen. I'll have lots of CO which can be order of to 5% or so. Okay, we have some measurement of CO. Sometimes we have found CO in old ambassador car of 70s or something up to 8%. Okay, so that you see here, and as you supply more and more oxygen, almost up to stoichiometry, you see the emissions are going down. Fair enough, simple thing, but then the CO emissions will reduce depending on where you are. Okay, look at the hydrocarbon. Okay, now we are in the measurements of ppm. Again, what you are doing is you are putting more and more hydrocarbon. Hydrocarbon is reducing because you are able to burn more and more hydrocarbon, but it does not really go very low, okay, like CO, because their emissions, as we said, that it can vaporize before it can burn, something like blow by or something, or the emissions can continue to happen, and it may reduce to at this point to minimum, but it doesn't go so minimum also. Okay, and then there's a little tendency here that it may go up. Why? Because now you are putting that even the fuel, there's not enough of the fuel not able to burn, so chances of the unburned fuel also escaping become larger and larger here, because you are not even, you don't have enough things to burn. And here, in fact, even if you go so low, below 20 or something, you may not even able to fire, because you have made your mixture very, very lean. Okay, if you have made it very, 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 very lean, then hydrocarbon might just escape, because you are not even able to burn. And this side also you may not be able to burn anything if you have just the fuel and not the oxygen. Okay, so these are the two extremes. Okay, engine cannot operate beyond this, engine cannot operate beyond this. So you see how the hydrocarbon emission will continue to be there. It doesn't go zero so easily. Okay, NOx. Okay, and obviously we have discussed a lot NOx about this thing. So as you go higher air to fuel ratio, something like this, it will peak here, and that equivalence ratio will be close to 0.9. Okay, and we also have explained the reasons as to why the NO or NOx for that matter will come down. Okay, so if you are operating your engine somewhere here, there are lots of NOx emissions. Okay, that I have explained you earlier, but that also is very clear. Let's see, we'll complete this, don't worry. If I have to produce, I have to also, the water is being produced, so I can also show how the water will change. So this water will change something like this. Okay, increase, it will go up to here, and then this water will decrease. Why will it decrease? Water also you can think in terms of the percentage. Why the water would decrease? Because of simple dilution effect. You have more and more air. Okay, these are the all concentration units. Okay, so it will peak up to there, and after that there is more air I am drawing in. Air to field ratio is becoming higher, so the concentration will decrease. Probably the mass is the same. In fact, mass is the same, but the concentration will decrease because I am putting more and more air. Okay, so you see here it'll probably will decrease. Okay, and oxygen. There is no dilution for the oxygen, but at some point oxygen will it continue to rise, the concentration of the oxygen, or at some point it will stabilize to the atmospheric oxygen, right? Okay, it will be in percentage. So maybe if I go a little bit more this side, it will become stable, right? Agreed? So that I can draw this one and everything. Okay, before we go to the next slide, normally, okay, my petrol vehicles operate somewhere close to here. Okay, okay. It means I'm really supplying less oxygen than, because you want the good pickup and good this thing, so we get this thing. So if I ask you, what are the issues with the petrol engines? Okay, your answer will be carbon monoxide and hydrocarbons. Okay, not so much of NOx. Okay, you agree or you disagree? Sorry, carbon monoxide. Sorry. No, if you come this side, okay, somewhere here. So, see, the carbon monoxide is again in percentage, so it's not small, 1.52%. The units are in percentage. All right. So, and let's see the issue in the relative sense. Okay. So, if I am operating my engine somewhere here, okay, then I am likely to get huge amount of hydrocarbon, right? Huge amount of CO for that matter, in the relative sense, not so much of NO, right? Okay, agreed. So look at how the two engines with different will give you different emissions. Okay, and as I operate onto the diesel side somewhere here, okay, I get lots of power, I get lots of energy. I can drive the huge trucks and I can drive huge like locomotives and things like that. But you see here, maybe hydrocarbon not so much a problem. Okay, CO is almost, in the diesel truck you go and measure, you will not get any CO. Okay, but what will you get? Huge NOx. NOx is a serious problem with the diesel engine. And the other thing is also the smoke from the diesel engine. That we'll talk maybe in the next class. But you can see how, with little this knowledge, okay, the stoichiometry, this thing, and we can deal properly with the petrol-driven vehicles and the diesel-driven vehicles. We can set the standards for the petrol-driven vehicles. If for the petrol-driven vehicles, you set the standard, oh, NOx should be less than this. Well, where is the problem? NOx should be. Oh, they'll say they are all happily. But then you have to set the standard for CO and hydrocarbon for the petrol vehicles. So in fact, if you see in the regulation, okay, or so-called Euro 1, Euro 2, Bharat 1, Bharat 2, you all are aware of Bharat 1, Bharat 2, Bharat 3. You say, okay, Bharat 1, Bharat 2, Bharat 3 for the petrol-driven vehicles. So then they'll say, well, CO and hydrocarbon. Okay, Bharat 2, 3 for the diesel-driven vehicle. Then you will see largely it will be about the smoke. Okay, because diesel produce smoke that we have not discussed in the class, but huge amount of NOx. I don't think that we have a summary here. What else is drawn? CO2. How have we done about CO2? Where is the CO2 going on?
Thin line.
This one?
Yes.
Okay.
Yes.
So that also you can say it should correspond with the CO. CO decreasing, CO2 will increase obviously, and after some time what will happen is that because of these are all dilution effect, more oxygen, more air, so that will kind of thing. So this is a very important thing which we learned today. Something more? Oh, okay, that was the question here. Diesel, and then summary of the figure 1. More summary. Well, we got it wrong here. This is also not so much of hydrocarbon, which a little comparatively. NOx is high, soot is high. The soot is low here, okay, and hydrocarbon is low here. Okay, that sometimes hydrocarbon can be more in the diesel engine because you're going up and you try to push more and more fuel, which cannot even burn, and that thing can come out. We'll stop here.